In this video, we're going to continue to look at the central limit theorem. So this is part 2 of our central limit theorem. So first off, our theorem from before was for a normal probability distribution, let x be a random variable with normally distributed who has a mean and standard deviation. And then our sampling x bar distribution, taken of size n, our distribution is normal, our x bar distribution has a mean of mu, and our standard deviation is sigma over square root of n. And we looked at this example of how that would work out. Now, what we want to consider is what happens if our distribution is not normal. What happens if the thing we start with, our original parent population, one is we know it's not normal. It could be skewed. It could be uniform. It could be custom where I just make it whatever, right? It's some weird thing. What happens if it's not normal? What can we do? Well, let's look at a skewed. So we'll start with a sample of 5. And if we do the same thing, take a sample, plot the mean. Take a sample, plot the mean. Take a sample, plot the mean. Or if we do this 10,000 times, we get to here. So you'll notice from this skewed example, our mean is still very similar. Standard deviation got smaller, about the same. But it's still a normal distribution. What about if it's uniform? There's no normal curve, bell-shaped curve at all, and we do 10,000 samples. We also get a normal curve. And if we have some other random-shaped curve and we take it, we end up with a normal curve. So what happens if the original is not normal? And this is where our central limit theorem comes in. So here is what the central limit theorem tells us. If x possesses any distribution, so if we have any distribution, skewed, uniform, something crazy, with a mean and a standard deviation, the sample mean x bar, based on a random sample of size n, will have a sampling distribution that is normal with the same mean and the same sigma divided by square root of n. So it doesn't matter if our original distribution is normal or not. This will still work. That's the central limit theorem. Okay, and we are not going to use the z. We're just going to do it on the calculator when we do that. Now, we do have to be careful with one thing. How large of a sample should we have so we can be confident that this works? And the general notation that they use is for most distributions, we want a sample size of 30 or larger to say that the distribution is approximately normal. So generally the way we look at this, we say if the original distribution is normal, any sample size will work. If the original distribution is not normal, we need a sample size of over 30. So if you go back to what we did yesterday, you'll notice for this problem, we only had a sample size of 9. But if you read the original problem, it says they were normally distributed. So because they were normally distributed, any sample size would work. Okay? If you do a problem that it doesn't tell you anything about the original, it doesn't tell you if it's normal, it doesn't tell you if it's skewed, it doesn't say anything, then, or it tells you it's not, then you need a sample size over 30. If it doesn't tell you anything, and the sample size is less than 30, you just write not possible, because we can't do that with the central limit theorem. So let's look at an example. The average age of a vehicle registered in the United States is 8 years, or 96 months. Assume the standard deviation is 16 months. If a random sample of 36 vehicles selected, find the probability that the mean of their age is between 90 and 100. Now notice, this doesn't tell us anything about the original distribution. Doesn't tell us anything is normal. But because our sample size is bigger than 30, we are okay. So we have our mu x bar is 96. Our sigma x bar is 16 divided by the square root of 36, which is 16 over 6. So we write this as we have 90 x bar per 100. We want to focus on what's our variable. Is it x or is it x bar? And then we can go to our calculator, and this is just normal. CDF of 90, 100, 96, 16 divided by 6, and you can put that in your calculator. So what you're really doing on these problems is you're deciding a couple things. One, can you do them? Is your sample size big enough if you need that? And then two, what's the standard deviation? That's the only thing that's really changing in these examples. Let's look at an example. A.C. Nelson reports that children between the ages of 2 and 5 watch on average 25 hours of TV per week. Assume the variable is normally distributed and the standard deviation is 3 hours. Is normally distributed, our sample size does not matter. So we can have any sample size. Find the probability that a randomly selected child watches more than 29 hours a week. So first we have to decide what's our variable. A randomly selected child. That, more than 29, is just an X bar. B, if 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean number of the 20 is greater than 29. So that would mean X bar is greater than 29. If X bar is greater than 29, if we now put these in the calculator, we will have normal CDF 29, 99999. Our average is 25 and our standard deviation is 3. And if we do that, we get 0.0912. And then if we do this for our sampling distribution, almost the same thing. 29, 999, 25, and now we have 3 divided by the square root of 20, but we get a very different answer. We get 0.04. Very, very small number. On the calculator, it actually got that. Now, why does that make sense? Well, if you think about the distribution here, if we draw our normal curve, the mean's at 25. 29, what's the probability we get more than 29? Well, when we have our just normal 3 standard deviation, there's going to be some up there. But when our sampling distribution and we divide by the square root of 20, our standard error gets much smaller. So what happens is, if you remember, this graph gets much, that was not very accurate, this graph gets much narrower. So the amount that is less than greater than over 29 up here is much, much, much less, because your sampling distribution, when you're finding the distribution of the means, you have a much smaller standard deviation, the standard error. So the graph is much narrower.